Hello everyone. This video is about some examples on the notions of basis and dimension of vector spaces. The first example I want to mention is just a recalling from the last video where we had a matrix A with 4 columns, A1 through A4. We checked that the first 3 columns were in fact sufficient to generate the column space of A. So we checked that the column space of A was the span of A1, A2, and A3, and in fact, that A1, A2, and A3 were a basis for the column space. Similarly, we found a generating set for the null space of A, which was given just by a single vector, 4/3, 2/3, minus 1/3, 1, which turns out to be a basis. I remind you that a basis is a linearly independent generating set. Let's move on to new videos, new examples, not the one from the last video. Have a look at this subspace here. The space V is the set of vectors in R4 defined by their entries satisfying this particular relation between them. Our goal is to find a basis for it and to determine what its dimension, what is its dimension. To find the basis, well, first observe that every element in V must have this relation between its first entry and all the others. We get this by just manipulating the equation that defines V. Move everything to the second side except for x1. In other words, that means that I could write this vector as 2x2 minus 3x3 plus 4x4. And then x2, x3, and x4. If I wanted to expand on the contribution of every one of x2, x3, and x4 in this vector, I could put them in evidence by factoring them out as follows. x2 only appears in the first entry with the coefficient 2, and in the second entry with a 1. x3 appears with a minus 3 here, and then it's 0, 1, 0, and x4 is 4, 0, 0, 1. So what we've done here is write every vector in V as a linear combination of these 3 columns, 2, 1, 0, 0, minus 3, 0, 1, 0, 4, 0, 0, 1. In other words, what we wrote is that V is the span of 2, 1, 0, 0, minus 3, 0, 1, 0, and 4, 0, 0, 1. Writing V as the span of these tells us that these are a generating set. But now the next question is, are they also linearly independent? And we have done most of the work needed for the answer. Any element in the span of these 2 vectors looks like this. So my question is now, is there a way to write 0, the 0 vector, as an element in the span of these 3 vectors, 2, 1, 0, 0, minus 3, 0, 1, 0, 4, 0, 0, 1, without the coefficients all being 0? Well, you see that if you write the 0 vector like this forces immediately x2, x3, and x4 to be equal to 0. In other words, if you write it as a linear combination, the 3 coefficients must all be 0, which is saying that these vectors are linearly independent. And so we found a generating set which is linearly independent. In other words, these 3 are a basis. Of V. And as a conclusion, since V has a basis containing 3 vectors, then the dimension of V is exactly 3. Let's move on to the next example. Here we're given a matrix and we're asked to find a basis for the null space of the matrix. Now, the null space is defined as the set of solutions of the homogeneous linear system associated with the matrix. So to solve that linear system, we augment the matrix A with a column of zeros, and we compute its row reduced echelon form. It's written here. From the reduced row echelon form, we can read off the solution space to our system. In particular, we read that x1 minus 2x2 plus x4 is equal to 0, and x3 plus 2x4 is equal to 0, and that x4 and x2 are free variables. Packaging this information into vectors, we see that the general solution looks like this. x1 is equal to 2x2 minus x4. Then we have x2. x3 looks like minus 2x4. And then we have x4. In other words, we can write this isolating x2 and x4 as follows. x2 has a 2, 1, 0, 0, and x4 appears with minus 1, 0, minus 2, 1. This is to say that the null space of A is generated by the two vectors 2, 1, 0, 0, and minus 1, 0, minus 2, 1. Now, two vectors are linearly independent as long as they're not one the multiple of the other. So these two are also linearly independent, and therefore we found a basis of the null space of A. Since the basis contains exactly two vectors, the dimension of the null space of A is equal to 2. This is not a coincidence. This 2 here is equal to the number of free variables. In other words, is equal to the nullity of the matrix A. We'll think more about that in the future. Let me just comment very briefly on one kind of procedure that you may encounter in the future, which is, suppose that you are given a set of vectors of a certain space, and you want to check whether those vectors are bases for a certain subspace. So when you want to check that a set S is a basis for a subspace, you need to do three things. First of all, you need to make sure that all the vectors in S are vectors in V. It can't be a basis of V if some of its vectors are not in V. And then there are the two checks of the definition of a basis, which is that S is a generating set, so we need to check that S generates V, and S is a linearly independent set. Another type of technique, we'll see an example of both later, is the answer to the following question. Suppose you have a vector space and you know its dimension, you know it's k-dimensional. And then suppose that you have k elements of V. What can you conclude if you know that those k elements are not a basis of V? Well, since S is not a basis of V, this means that either S is not, well, it's either linearly dependent or S does not generate V, but it is linearly dependent. But it is linearly independent. These are the only possible two cases. However, in this second case, if S is linearly independent, then by the property of the basis, then it can be extended to a basis. I believe this was property 2 in the previous video. However, this is a problem because S has k vectors in it, and the dimension of V is equal to k. So this cannot be. There is no way that we can extend S to a basis because that basis will have more vectors than the dimension of V. So S cannot be extended by dimension reasons. In other words, by this argument here, we must exclude this possibility. So the only possibility that is left is that S is in fact a linearly dependent set. The more general statement about this sort of question is the following. If you have a k-dimensional subspace, it's important that you know the dimension, and a set containing k vectors, then there's only two possibilities. Either this set is a basis for the subspace. If it isn't, it is linearly dependent. Let's conclude with one last example. Here's a set V, a subspace of R3, defined by this condition of its entries, V1 minus VT2 plus V3 is equal to 0. And here's a set of two vectors. Let's check that S is a basis for the space V. Well, first of all, we need to check whether the two vectors do belong to V, minus 1, minus 2. So let's write out the relation that we require for these to hold, minus 1 plus minus 2. This is 0. So the first vector does belong to V. Let's do it for the second, 2 minus 1 minus 3. When I write that, I get 2 minus 1 plus minus 3. And if I add them together correctly, I also get 0. So indeed, all of the elements of S are inside V. Let's check that S generates V. We can use the same trick as before. If an element is in V, then we can write this element as follows. Maybe getting rid of the first variable, V2 minus V3, V2 and V3. So we can write it as a span of, well, V2 as 1, 1, 0, and V3 is minus 1, 0, 1. Okay, so we wrote V as the span of these two vectors. Now, the question is, can we get 1, 1, 0 and minus 1, 0, 1 from our set S? If the answer is affirmative, then S generates these two generators, and so S is itself a generating set. Let's try. For example, if I take the difference between the elements of S, minus 3, this becomes 1 minus 2, that's minus 1, minus 1 minus minus 1, that's 0, and minus 2 minus minus 3, that's 1. So we get one of the two generators. To get to the other, what could we want to do? This is a work of a little bit of guess and check. I want to get 1, 1, 0. So for example, if I subtracted, let's see, I take 1 minus 1 minus 2, and then I subtract this newly found vector here, which I can use because I generated with the ones that I just have been working with. Will this work? Let's see. Let's do plus 2 that. What happens now? I get 1 minus 2, so that's minus 1, and I get negative 2 plus 2, so that's a 0. That's not quite the vector I wanted to get, but it got me close enough that I can take a guess. And maybe I can make a minus here and a minus here so that all the signs are changed. And when I do that, I do get my second vector. So I was able to use just the vectors 1 minus 1 minus 2 and 2 minus 1 minus 3 to generate the two sets of generators that we found here. In other words, these two vectors are a generating set. The last check that we need to make is linear independence. And for this, we want to write 0 as follows. Well, these are two vectors, 1 minus 1 minus 2, and 2 minus 1 minus 3. Two vectors are linearly dependent only if one is a multiple of the other. These two are not multiples. Of one another, and therefore they are linearly independent. This is a more subtle question when there's more than two vectors involved, but in this case, it's straightforward to see that you can't get one by multiplying the other by a scalar.